Thank you for joining. Well, I will take, there is some overlap with the previous talks. I'll talk about Sentinel data, which was discussed in the first talk, PDS. And I'll be mentioning convolutional neural networks, which was in the talk just before. So the agenda, I should first want to describe a project which was used as an instigator for this quantum computing project. And then I will dive into the convolutional neural network algorithms. So the goal of this talk is to describe the quantum convolutional neural network algorithms that are the potential solutions for a problem we found in Earth observation. So in the Earth observation, the CS group has a big experience, and one of the projects we have managing now for CNES, the French space agency, is IOTA 2. So this is a machine learning framework. The goal of this framework is to map the land over a large area, typically a country, and the mapping of the land, that means identifying what is field, what is industry, what is river, what is forest, etc. And IOTA 2 manages optical data. This is data satellite images from the Copernicus satellites in the Sentinel-2 project, and covers a large spatial area, so typically a country. And spatial stratification is, it can make the differences between a field in one part of the country and a field in another part of the country. They have different characteristics. So the typical images that come into the are 10,000 by 10,000 pixels. Those are the satellite images with 23 classes. And one run covers the whole year, typically 60 to 70 images per tile, and around 100 tiles over the country. The software is run on the HPC environment of CNES, so they have a 10,000 core, 16,000 core machine to run this type of jobs. So the classification in IOTA 2 uses now random forest and the support vector machine classifiers. These are in OTB. OTB is a package managed by CS Group for CNES. And but IOTA 2 also supports scikit-learn methods. So it supports object-based image analysis, so that an object is a set of pixels. For instance, you can have a set of pixels as part of the river, so then you can create an object river. And you can create an object building with pixels in that building. And it supports out of context. That means that the context of objects can be used to classify the object itself. So it uses the classifier uses the context. So now the plan currently is use random forest or SVM. The plan is to use neural networks, and there we think that the training times will become prohibitive on classical systems. You have to think that the random forest classifier runs about 1 hour on a 24-core node, and we've done tests with a small part of the data set, and with a neural network we were already going over 10 hours of training. So this was one of the reasons to say, let's see if quantum computing could be a solution for this problem. So this, just to summarize, the amount of data is increasing enormously, and the training times become prohibitive, so these are the reasons for this project. Going into the tests that have been done in this project. Firstly, the test data set is a Eurosat data set. It's available on GitHub, open source, and it's with Sentinel-2 images from the Copernicus satellites and 27,000 images. And I've got the link for the GitHub. If you want the slides, please, I'll leave my cards here. You can always get them from me. So the classic, this is just a scheme of the CNN, which a previous speaker also already described, with the convolution, pooling, and fully connected layers. I'll just dive into the quantum bit. So just some basics. So the what is the difference between classical and quantum computing? In classical, you have a bit, 0 or 1. The qubit quantum is a vector, and a vector which in that sphere that is shown on the slide. So the 0 is the top level of the z-axis, and the 1 is the bottom level of the z-axis. Then the qubit is a combination of 0 and 1. It's alpha 0 or beta 1, with alpha and beta are complex numbers. So any vector on that sphere, that is the qubit. Can be any of the vector. So there you see the principle of superposition, where you have a bit of a 0 and a bit of a 1. And a quantum circuit performs an operation on that vector. So for instance, you can have a rotation around the z-axis with angle theta. That is a circuit quantum operation. You have to think about it in the term of classical. It's like you're going down at assembler level and you're really touching the bits and telling them what to do. This is with the quantum, you have this, you're telling the qubit how you're going to move around this sphere. Another principle is superposition. Superposition, if you have one qubit, you have a bit of a 0, a bit of a 1, so you have two states, combination of two states. If you go to n qubits, you have 2 to the power n states that you can put in parallel. And that is also the amount of data you can put in the qubits is grows exponentially. That's a big difference with classical systems. 2 qubits can be intricated. Intrication means that 2 qubits, if you know one, the other one is kind of linked to it. And if you have many qubits, they can all be linked to each other. You have to think it, visualize it as if it's superconductivity. In superconductivity, if all the spin is going one way, and then that means the resistance is 0. And that is a characteristic we will use in quantum computing. Okay, what was the development strategy? Is to the ultimate goal is not to have the whole algorithm in quantum space, because you have to think that when you go from quantum to classical, that's where you lose time. So you try to have everything in quantum space, and only at the end have the result coming back to classical space. And another thing is you want, if you want to store the maximum data on your qubits. So what I want to describe to you is one way to gradually increase the quantum portion of the algorithm. Note that we make use of published algorithms. So this is also a bit of a literature survey. First we add a single quantum layer, then we put the CNN in quantum space, the optimization in classical space, and then the whole thing over. First, add a single quantum layer to the CNN. So CNN, here we have a CNN with 3 levels, so 3 times convolution, ReLU, and pooling, and at the end how do you call it, a totally connected layer. And on the top you have the classical, where you have the from the fully connected layer you choose class 0 or class 1, and in the quantum you put in between you put a quantum layer with a rotation of the qubit along the x-axis, and the angle theta is then the parameter. So this is one way of putting layer. You can also make more complicated layers, but just to explain, it is a parameterized layer. And the parameter is what the operation that you put on the qubit. The implementation was on Python. We used PyTorch with a Qiskit API, and the number of qubits 1 to 4. And we ran it on the IBM simulator. Note that the code itself can then be run either on IBM, quantum computer, IonQ, or Rigetti. Those are the three that support Qiskit. Just the reference, I mentioned it was inspired by Sebastian. Already? I have 11 minutes. I have 18 minutes. No, I have 7 minutes.
No, 15 minutes plus 3 questions.
Okay, so let's. So this is just to show you that the quantum and the classical have similar accuracy. If you go to a bit, now the second model is the where you have the model in quantum space. And here I have put the data preparation encoded in qubits using the cluster state model. The convolution, this is the circuit for the convolution. This is just a set of parameterized rotations of the qubits. The pooling is also parameterized rotations, and in the middle there is a C0 gate. And the C0, that is the one that pools the n qubits in n over 2 qubits. But then finally at the end what we do is a classical optimization. And just to show you, again there's some details of the implementation, but the results we got was about 80%, which is, well, it's only one convolution and one pooling layer. It's at least it's not as good as the previous, it's not as good as classical method at the moment, but the potential is there. And one of the issues we had is that the TensorFlow Quantum did not have an elaborate QRAM function, so we couldn't put all the data into the qubits efficiently. So I just want to mention then the next step, the third algorithm is inspired by Kerenides' work. So there we write the convolutional neural network algorithm in terms of linear algebra operations. So that's matrix, vector, etc. And the idea is that the linear algebra operations map very elegantly onto quantum operations. And so we use that characteristic to create a forward pass, the update with the quantum pooling and the quantum backpropagation, all in the quantum algorithm. This is what we aim to do. We haven't done this yet. Just to show you that this is a logical next step. And then if we manage to do that, then the advantages we expect is firstly that we use all the log n qubits for the input of n pixels. So we manage to put all our data on a limited number of pixels. And the algorithm itself would scale order n in the quantum version instead of order n squared as a classical version. So there we have a polynomial speed up. And potentially in higher accuracy. But there have been cases in the literature where the accuracy is better with a quantum algorithm than with a classical algorithm. So conclusion, so the field of quantum algorithm is thriving. There's a lot of algorithms that are being published. There's been work actually over the last decades on this field, but now that the quantum hardware is become available, suddenly all these algorithms becoming very actual interesting. But we know that to go to the quantum machine you need to rewrite your algorithm, but we can potentially solve very big problems as the amount of data and the increase of training times. So for more details, You're welcome to get my card. Thank you very much.
Thank you. Questions? Yes?
So how do you exactly encode an image? So suppose you have the fully quantum network.
Yeah.
How do you encode the image? So as an input of the network in terms of qubits.
Qubits. Well, there are several ways to do that. So one of the ways is to use the, if we go to this table, is to use, if you have, for instance, 16 qubits, 4 by 4,
Mm-hmm.
right, and each qubit has 8 bits. So you keep 8 qubits for the value,
Mm-hmm.
and then you use 4 qubits for the index. So then you have 12 qubits because but then so the value qubits stay the same, but if you increase the number of pixels, like go to 1024, then you have 10 by 10, then you have 16. You have 1024, is that 10 by, no, I got something wrong. 2 to the 10s, sorry, 2 to the 10s, then you have 16 qubits, you need 16 qubits. So what you do is you keep the number of qubits for the values the same, but you only increase the index qubits.
One quick question? If not, let's thank Matis again and all the speakers of this.